Hey everyone, I'm here with a quick review about isomers, and again this is for the ACS exam, just a really quick one. We have different kinds of isomers. Usually on an exam you're given two molecules, and if they're the same formula then you have to think about how they're related to each other. And either they could be identical molecules, like here I have 1, 2, 3, 4, I have N-butane in both of these examples, but they're different rotations or three-dimensional structures of butane, so they're actually different by rotation only, so that means they're really the same molecule though, but just different behavior depending on, its different conformations. So that's called conformational isomers or rotamers, but again, the same molecule, they're both called N-butane, and so we're just looking at different snapshots in time. And you may recall from chair conformations, depending on what groups are axial or equatorial, you might have one conformation favored over another. That means the molecule is maybe considered more of one type of isomer than another in terms of what shape it looks like most of the time. So that's helpful to analyze that. So we'll come back to that. Stereoisomers are ones that are almost the same molecule, but not really because they have a chirality to them. Like here we have two stereoisomers, which are an example of enantiomers. Enantiomers have a chiral center and they are mirror images of each other that don't superimpose. These are different molecules. So you'd know one of these is called S2-butanol and one of these is called R2-butanol. So we'll review that. And then stereoisomers can also be geometrical in nature, meaning I don't have a chiral center in these two butene molecules, but they're clearly different molecules. Because I can't just rotate them. They're not conformational. They're actually fixed in this orientation by the pi bond. And in that situation, we don't have mirror images, and yet they're still stereoisomers in the sense that they're both 2-butene, but spatially they're fixed to be different molecules. So I have cis 2-butene and trans 2-butene, and those are called diastereomers because they're not mirror images of each other that are non-superimposable, whereas these are. So I have stereoisomers, enantiomers, and diastereomers are types of stereoisomers. So we'll review that. And then these could be, well, that's where Meso comes in, and so we'll talk about that too. Constitutional isomers are the most different. They are different connectivity of the atoms, so they're going to have different chemical properties oftentimes, or different physical properties. So here this is isobutane versus N-butane. So it's good to know some of the vocabulary. So thinking about each one of those, let me just give you some tips. Sometimes on an exam, you might see something like this versus something like this. And you might be asked, how are these related to each other? Okay, so just looking at these off the bat, they're both cyclohexanes and they're both trans, but are they the same molecule? So what I would do is probably sketch it in a more planar format, and I'll consider this up or sticking out, and I'll consider that's the opposite of whatever I chose before. And whereas this one will become, let's say this is up, and now next door to it to the left is sticking down. So really I'm comparing these two, right? If you have a hard time seeing chairs, and I know some of you do, you can't just say because they're trans, they're both the same. And that's because I have chiral centers here. And of course, they could either be the same or they could be mirror images of each other. And so to figure it out, I will label, carbon 1 and 2 could be like carbon 1 and 2 here. And you can see 1 has inverted stereochemistry and so has 2. So because all chiral centers have inverted, dash goes to wedge or wedge goes to dash, these are going to be mirror images of each other. So these are going to be called enantiomers. Now one stereoisomer that I've neglected here is this one. Maybe I have a different arrangement of those OH groups. Maybe something like this. And so how is this related to this, and how is this related to that? So clearly they're all stereoisomers of each other, but the vocabulary we use is different because one of these stereoisomers, one of these chiral centers stayed the same, but one of them inverted. It's not an enantiomer of these two, so we can't use that term. In fact, we have two chiral centers, one of which is inverted, or you get partial inversion, maybe 3 out of 5 invert, or 1 out of 2 centers invert in this case. You can't get a mirror image then unless they all invert in their configuration. So this is considered diastereomer when you don't have all the centers inverted. When you don't have, it's not a mirror image, but it's clearly a unique stereoisomer. It does count as a stereoisomer. Now when we think about that to this, if there are diastereomers, this to this is also a diastereomer pair. Okay, so this to this is related by being a diastereomer. There's one more stereoisomer that I want to show you as well, and that's this one. So you might think that these two are enantiomers of each other because we have inversion at both stereogenic centers. But do you guys know that actually these two molecules are the same? And either you can visualize it, you can visualize flipping this over, then these both wedge or dashes become wedges, or you might notice that there's a plane of symmetry, internal plane of symmetry, like that. And because of that plane of symmetry, these are considered achiral molecules. This is one molecule, they're identical, and they're both achiral. So even though they contain chiral centers, those centers their chirality sort of cancels out because of that internal mirror plane. And in that situation, it's achiral, but it has chiral centers within it. That warrants a special name called Meso. So that's when we have a Meso compound, when we have chiral centers, but the symmetry causes it to be achiral. Okay, so what I'd like you to do is picture, use the terms I threw at you earlier. Okay, one of these is more different than the others, and I want you to point out what pairs are. Let's say, give me an example of two molecules that are constitutional isomers of each other, two molecules that are enantiomers of each other, and two molecules that are diastereomers of each other. Okay, so, and there's multiple answers might apply, so see if you can find them all. And I'll give you a chance to look at that and pause it and come back. All right, so you guys can see one is really different from all of the rest. All of the rest are stereoisomers of each other, but one is a constitutional isomer of any of these other four. So an example would be 1 and 2 are constitutional isomers because here we're connected to 2 hydroxyls, but here we're connected to 1 hydroxyl here and 1 hydroxyl there. So connectivity is different. Enantiomer-wise, you could probably see who the mirror images are. You could see 3 and 5 are mirror images, but also you could have said 2 and 4. They're not the same molecule. And the reason why is you can see that these two groups, when these two groups are the same, you could have symmetry, but these two groups aren't the same, so you don't have that symmetry. So that means this is chiral and this is chiral, and there is no internal plane of symmetry. So these are enantiomers of each other, and these are enantiomers of each other. And then any other combination, like 2 and 5 would be diastereomers, or 3 and 4 could be diastereomers. So basically they are stereoisomers, but they're not complete inversions of each other, so they're not mirror images. That's the word we give to diastereomer in the context of optically active molecules. But in the context of like geometry, diastereomers could also apply for cis-trans. So we use the term diastereomer several different ways. Now let's quickly review R and S configuration. And I mentioned before that you could have 2 butanol 2 different ways. So one of these is S and one of these is R. Here's one. So I'm looking at this chiral center, and I'm looking at the 4 things attached to it. Okay, and don't forget about that H. So this is, we go based on mass. So this is chiral center, has an oxygen, a carbon, and a hydrogen. So, and then this carbon is attached to the next heaviest one is a hydrogen, and here the next heaviest one is a carbon. So because those two, this one wins, this will be my number 2, this will be my number 3, and hydrogen is usually number 4 in the bag. So if I have this 1, 2, 3, I follow that around from 1 to 2 to 3. And if you go clockwise with 4 is in the back, and if you go clockwise, that's going to be R. So that's what I remember. And then anything that's opposite of that is going to be S. So in this case, I have 1, 2, 3, like that. So it looks like R, but hydrogen's in the front, so I reverse it. 4 is in the front, and then we go, if 4 is in the front and we go this way, that's going to be S. So the rules switch here. So notice depending on where number 4 is. And so just either learn this one or learn this one. You don't have to learn both, but it helps a lot. Another one is a little bit more complicated when you have like double bonds and things. Okay guys, so let's say we have this weird acid halide carboxylic acid amino compound, and here's my chiral center. So I'm looking at who's attached to that chiral center, and immediately the nitrogen is heavier than carbon, so nitrogen group gets 1. So I'm not looking at the mass of the whole group, I'm just looking at the mass of the first atom attached. Here I have, and then clearly hydrogen's 4. And then here I have sort of a tie, right? And so they both have double bond O, but O is not the heaviest one on all of these carbons. It's actually bromine. So bromine makes this carbon win. So I just have to look one atom at a time, carbon, carbon, tie, look at the next heaviest one, and then look at the next heaviest one. And then you could break the tie that way. So this will be 2 and this will be 3. Now let's change this a little bit because I want to show you what happens with these double bonds. It's a little tricky sometimes. Okay, let's say I have something weird like this, and then so that means that I'm looking at, carbon has oxygen, oxygen, and nitrogen, but this double bond, the way that we consider that double bond is we sort of think of it like carbon's bonded to 2 single oxygens. So we split that double bond into 2 single bonds, and we bond it to the same thing. So carbon double bond to O is like carbon single bonded to O and another carbon single bonded to O. And then this oxygen was attached to carbon, so we consider doing this to make up for that on the other end. Isn't that sort of weird? The carbon's bonded to 2 bonds to oxygen, so 1, 2. And then this oxygen's 2 bonds to carbon, so 1, 2. So it's sort of weird. But that's the way that we sort of count it. So now looking at carbon, they tie. The next heaviest one is oxygen. This one has oxygen. This one has oxygen, this one has oxygen. And then it comes down to this guy here, this nitrogen versus this oxygen. So then this one would win because oxygen's heavier than nitrogen. So in this case, it would be 2 and then 3 over here. Okay, so it's sort of strange, but that's sort of how we deal with these double bonds and triple bonds too. Another thing I'll mention is that with these Fischer projections, it's good to remember that the horizontal lines going across, these are your wedges, okay? So if I'm looking at what is the configuration of this carbon here, is it R or S, I'm going to look at 1, then this whole group down here is my 2, because I have, it's good to draw out the, let's draw out the aldehyde. And then I'm looking at this carbon versus this carbon, and then this carbon has 1 oxygen, and this carbon is sort of like 2 oxygens. So this group will be considered 2. This whole thing will be my 3rd, and then hydrogen will be 4. But now here's the thing with Fischer projections, 4 is in the front, because these lines going across are actually wedge. So 4 is in the front, H is in front. So now I have to switch my answer. If I memorized that clockwise is R, but 4 is in the front, then I have to flip it to S. So 1 to 2 to 3 is counterclockwise, which I would normally think of as S, but because 4 is in the front, it switches everything. So S turns into R, or counterclockwise turns into clockwise. Okay? So this chiral center right here would be R. Why don't you pause it and figure out what is the chiral center here, my next chiral carbon. Okay, so this is 1. This is 2, because this carbon versus this carbon is a tie, but this one has an oxygen, and then this one has an oxygen, and then this one has another carbon, and this one only has hydrogens. So this is 3, and this is 4. So 1 to 2 to 3, that looks like R, but remember 4 is in the front. So I'm going to switch it to S. Okay? So I have R and S like that. And the very last thing about stereoisomers is I just want to remind you, sometimes we use different kinds of drawings. So don't be weirded out by these. These are just side views, you know. Sometimes it helps just to reorient it. And if you're used to dashes and wedges, just, you know, redraw things, and don't feel too bad about doing that. Same thing with sort of like these Newman projections too. You know, get used to sort of, you know, if you can't see it right away, then maybe try redrawing it, you know. And so here's this front carbon right here, and then I have my eye. Let's say my eye is looking down that front. So here's my eye, and so maybe my hydrogen is right in front of me, and my oxygen's behind, and here's my H going to the top here. Okay, so you can sort of think of it that way, and then this might go over to the right, and now I'm seeing the carbon in the back, and my bromine's in the front closest to my eye, and my CH group is behind, right? So you have to have it behind. And then I've got another group pointing down right here, CH3. So it's just sort of like redrawing it might help you. And then let me sort of erase my eye so it's not so confusing. But so yeah, so I've got my bromine in the front with my hydrogen, and my methyl group in the back with my hydroxyl group. So sometimes it helps to just rotate it and then look at who's dashed and who's wedged. And sometimes that makes it easier for sort of figuring out what the relationships are, is to draw it in a different form that's a little more familiar to you. All right, so good luck with that, and you know, keep practicing it, and consider what I said about, you know, redrawing things into a form that makes more sense to you, just like we did earlier right here, and just consider the different ways of looking at it.